Part I, Introduction to IoT and Smart Infrastructure. Chapter 1, The Evolution of IoT in Infrastructure. Overview of IoT and its key components. The Internet of Things, IoT, refers to the interconnection of everyday objects and devices to the Internet, allowing them to collect, share, and analyze data. This network of devices, equipped with sensors, software, and other technologies, facilitates real-time data exchange and communication. Key components of IoT include 1. Devices and sensors, the physical objects equipped with sensors that gather data from their environments. These can range from simple temperature sensors to complex machinery with multiple sensors. 2. Connectivity, the means by which devices communicate with each other and with central systems, typically through Wi-Fi, cellular networks, or other communication protocols like MQTT or Zigbee. 3. Data processing, the analysis of the data collected by IoT devices, often performed in the cloud or through edge computing solutions. This includes data aggregation, machine learning, and analytics to derive actionable insights. 4. User interface, the platforms through which users interact with IoT systems, including mobile applications, dashboards, and web interfaces that display data and allow for control of devices. 5. Security, measures and protocols to ensure the integrity, confidentiality, and availability of the data and devices within the IoT ecosystem, addressing vulnerabilities that can arise from interconnected systems. Historical development of smart infrastructure. The concept of smart infrastructure has evolved significantly over the past few decades, driven by advancements in technology and the increasing need for efficient resource management. Key milestones in this evolution include 1. Early automation, 1960s–1980s. The automation of industrial processes marked the beginning of smart infrastructure. The introduction of programmable logic controllers, PLCs, allowed for more efficient control of manufacturing systems. 2. The Internet boom, 1990s. The proliferation of the Internet laid the groundwork for the interconnectivity of devices. This period saw the emergence of early IoT concepts, where devices could be monitored and controlled remotely. 3. Advent of wireless technology, 2000s. The development of wireless communication technologies, such as Wi-Fi and Bluetooth, facilitated the integration of IoT devices into everyday infrastructure. This era saw the rise of smart meters and initial smart city projects. 4. Mainstream adoption, 2010s. As cloud computing and big data analytics gained traction, IoT began to be adopted in various sectors, including transportation, healthcare, and urban planning. Smart grids, intelligent transportation systems, and connected buildings emerged as key applications. 5. Current trends, 2020s and beyond. The focus has shifted towards sustainability, resilience, and security in infrastructure. Innovations such as 5G connectivity, AI integration, and advanced data analytics are driving the next wave of smart infrastructure development. The role of IoT in modern infrastructure systems. IoT plays a transformative role in modern infrastructure by enhancing efficiency, sustainability, and responsiveness. Key contributions include 1. Real-time monitoring and maintenance. IoT enables continuous monitoring of infrastructure health, allowing for predictive maintenance that minimizes downtime and extends asset life. 2. Resource optimization. Smart infrastructure systems leverage IoT data to optimize resource usage, such as energy consumption in smart buildings or traffic flow in smart cities, thereby reducing waste and costs. 3. Improved safety and security. IoT devices can enhance safety in infrastructure by detecting anomalies, such as structural weaknesses or environmental hazards, and alerting relevant authorities. 4. Data-driven decision-making. The vast amounts of data generated by IoT devices empower urban planners, engineers, and policymakers to make informed decisions based on real-time feedback and trends. 5. Enhanced user experience. Smart infrastructure can provide users with personalized services, such as real-time public transport updates or tailored energy management in homes, improving overall quality of life. As IoT continues to evolve, its integration into infrastructure systems will likely expand, driving innovation and efficiency across various sectors. Understanding this evolution is crucial for stakeholders looking to leverage IoT in creating smarter, more sustainable environments. Chapter 2: Fundamentals of Smart Infrastructure. Definition and characteristics of smart infrastructure. Smart infrastructure refers to the integration of advanced technologies and data analytics into the physical structures and systems that support urban and rural environments. This includes transportation systems, utilities, buildings, and public services, which are enhanced by the use of smart technologies to improve efficiency, safety, and sustainability. Characteristics of smart infrastructure. 1. Connectivity. Smart infrastructure is characterized by extensive connectivity through the Internet of Things, IoT, enabling devices to communicate with each other and with centralized systems for real-time monitoring and control. 2. Data-driven decision-making. Leveraging big data analytics, smart infrastructure facilitates informed decision-making processes, optimizing operations and resource allocation based on real-time data. 3. Interoperability. Different systems and devices within the infrastructure can interoperate seamlessly, allowing for coordinated responses to various challenges, enhancing overall system performance. 4. Automation and control. Automation reduces the need for manual intervention by using smart sensors and actuators to manage operations autonomously, leading to improved efficiency and reduced operational costs. 5. Resilience and adaptability. Smart infrastructure is designed to be resilient to disruptions and adaptable to changing conditions, whether they be environmental, technological, or social. 6. Sustainability. Focused on reducing environmental impact, smart infrastructure promotes sustainable practices through efficient resource use, reduced waste, and integration of renewable energy sources. Key challenges in infrastructure monitoring and maintenance. Despite the promising capabilities of smart infrastructure, several key challenges hinder its widespread implementation and effectiveness. 1. Integration and compatibility. Existing infrastructure often consists of legacy systems that may not easily integrate with new smart technologies, leading to compatibility issues and increased costs. 2. Data security and privacy. With the increased connectivity of devices comes heightened vulnerability to cyber threats. Ensuring the security of sensitive data and maintaining user privacy are critical concerns. 3. High initial costs. The upfront investment required for smart infrastructure deployment can be substantial, making it challenging for organizations to justify the expense, especially when immediate returns are not guaranteed. 4. Technical skills gap. The implementation and maintenance of smart infrastructure requires specialized skills that may be lacking in the current workforce, creating a barrier to successful deployment. 5. Regulatory and standardization issues. The lack of standardized protocols and regulations governing smart infrastructure can lead to inconsistencies in implementation and operation, complicating management and interoperability. 6. Public perception and acceptance. Gaining public trust and acceptance of smart infrastructure initiatives is essential for their success. Concerns about surveillance, data misuse, and changes to community dynamics can hinder progress. Benefits of IoT-enabled solutions. IoT-enabled solutions significantly enhance the functionality and effectiveness of smart infrastructure. The following are some of the key benefits. 1. Enhanced monitoring and predictive maintenance. IoT sensors provide real-time data on the condition of infrastructure assets, allowing for predictive maintenance that reduces downtime and extends the lifespan of assets. 2. Improved operational efficiency. Automation and real-time analytics streamline operations, reduce waste, and optimize resource allocation, leading to significant cost savings. 3. Better resource management. IoT solutions facilitate more efficient use of resources such as energy and water by enabling precise monitoring and control, thereby promoting sustainability. 4. Increased safety and security. Smart infrastructure can incorporate intelligent surveillance systems, environmental monitoring, and emergency response protocols, significantly enhancing public safety. 5. Enhanced user experience. IoT technologies can provide users with real-time information and services, improving the overall experience in urban environments, such as traffic management systems that reduce congestion. 6. Data-driven insights. The vast amount of data generated by IoT devices can be analyzed to provide insights into usage patterns, infrastructure performance, and areas for improvement, informing future planning and investments. In conclusion, while the journey toward fully realizing smart infrastructure is fraught with challenges, the potential benefits of IoT-enabled solutions present a compelling case for continued investment and innovation in this field. The successful integration of these technologies promises not only to enhance the efficiency and resilience of our infrastructure but also to improve the quality of life for individuals and communities. Chapter 3: IoT Technologies and Architecture. The Internet of Things, IoT, represents a paradigm shift in how we interact with the physical world. It encompasses a wide array of technologies and architectural frameworks that enable devices to communicate, process data, and deliver insights. This chapter explores the foundational components of IoT, including sensors, actuators, edge devices, communication protocols, and the role of cloud computing and data analytics. 3.1 Sensors, actuators, and edge devices. 3.1.1 Sensors are crucial components of IoT systems, as they gather data from the environment. They can detect various physical phenomena, such as temperature, humidity, light, motion, and more. These devices convert physical parameters into electrical signals that can be interpreted and processed. Types of sensors. Temperature sensors measure ambient temperature and are widely used in vac systems and smart home devices. Proximity sensors detect the presence or absence of an object within a specified range, commonly used in automotive and industrial applications. Light sensors measure light intensity, often used in automatic lighting systems. Pressure sensors, used in various applications, including weather monitoring and industrial processes. 3.1.2 Actuators. Actuators are devices that perform actions in response to commands from IoT applications. They convert electrical signals into physical movement or changes in the environment. Actuators can control motors, valves, switches, and other mechanical systems. Examples of actuators: motors, used in robotic applications and automation systems to control movement. Solenoid valves, control the flow of liquids or gases in plumbing systems. Relays, used to switch electrical circuits on and off. 3.1.3 Edge devices. Edge devices are computing devices located at the edge of the network, closer to the data source. They process data locally and reduce latency by minimizing the need to send all data to centralized cloud servers. Edge device functions. Data processing, analyze and filter data before sending it to the cloud, reducing bandwidth usage. Real-time decision-making, enable local responses to sensor data, such as triggering actuators based on specific conditions. Improved security, by processing sensitive data locally, edge devices can help mitigate security risks associated with transmitting data over the network. 3.2 Communication protocols. Communication protocols are essential for enabling devices to communicate with each other and with centralized systems. Different protocols have been developed to meet the diverse needs of IoT applications in terms of range, power consumption, and data throughput. 3.2.1 MQTT, Message Queuing Telemetry Transport. MQTT is a lightweight messaging protocol designed for low bandwidth, high latency networks. It operates on a publish-forward/subscribe model, where devices can publish messages to a broker and subscribe to topics of interest. Key features: low overhead, minimal message size makes it ideal for constrained devices. Quality of service: CoS offers 3 levels of CoS to ensure message delivery. Retained messages, allows subscribers to receive the last message published on a topic. 3.2.2 LoRaWAN, Long-Range Wide Area Network. LoRaWAN is a low-power, wide-area networking protocol designed for long-range communication. It is particularly suited for applications requiring infrequent data transmission, such as smart agriculture and environmental monitoring. Key features: long range, can transmit data over several kilometers, ideal for rural and remote areas. Low power consumption, designed for battery-operated devices, extending battery life for years. Star topology, uses a star network architecture, where end devices communicate directly with gateways. 3.2.3 Zigbee. Zigbee is a wireless communication protocol designed for short-range, low-power applications. It is commonly used in home automation and industrial control systems. Key features: mesh networking, allows devices to relay messages, extending the network range. Low power consumption, ideal for battery-operated devices that require long operational life. Interoperability, supports multiple vendor devices, enabling a diverse ecosystem. 3.3 Cloud computing and data analytics for IoT. Cloud computing plays a pivotal role in IoT by providing scalable resources for data storage, processing, and analytics. It enables organizations to harness the vast amounts of data generated by IoT devices to derive valuable insights. 3.3.1 Cloud computing. Cloud platforms offer services that support the deployment, management, and scaling of IoT applications. These services include data storage, centralized storage solutions for managing vast amounts of sensor data. Computing power, on-demand resources for processing and analyzing data. APIs and SDKs, tools for developers to build and integrate IoT applications seamlessly. 3.3.2 Data analytics. Data analytics in IoT involves processing and analyzing data to extract meaningful insights. Techniques can range from basic statistical analysis to advanced machine learning algorithms. Analytics techniques: descriptive analytics, summarizes historical data to understand trends and patterns. Predictive analytics, uses historical data to forecast future events, such as equipment failure or demand spikes. Prescriptive analytics, provides recommendations for actions based on data analysis, optimizing operations and decision-making. 3.3.3 Real-world applications. IoT data analytics can enhance various sectors, including smart cities, analyzing traffic patterns to improve urban planning and reduce congestion. Healthcare, monitoring patient vitals in real time to improve health outcomes. Agriculture, using sensor data to optimize irrigation and crop management. Conclusion: the technologies and architectures that underpin IoT are diverse and constantly evolving. Understanding the roles of sensors, actuators, edge devices, communication protocols, cloud computing, and data analytics is essential for leveraging IoT's full potential. As IoT continues to grow, future advancements will likely enhance interoperability, security, and data processing capabilities, paving the way for more intelligent and connected systems. Chapter 4: Structural Health Monitoring, SHM. Structural health monitoring, SHM, is a critical component of modern infrastructure management. It involves the use of various technologies and methodologies to assess the health and integrity of structures over time. In recent years, the Internet of Things, IoT, has revolutionized SHM by enabling real-time data collection and analysis from a network of sensors embedded within structures. This chapter will discuss the role of IoT sensors in structural monitoring, focusing on vibration, strain, and temperature sensing, and will present case studies demonstrating the application of these technologies in bridges, tunnels, and high-rise buildings. IoT sensors for real-time structural monitoring. IoT sensors play a pivotal role in structural health monitoring by providing timely and accurate data on the condition of infrastructure. These sensors can measure various parameters, including 1. Vibration. Sensors that capture vibrations can help detect anomalies that may indicate structural distress or failure. By analyzing vibration patterns, engineers can identify potential issues before they escalate. 2. Strain. Strain gauges measure the deformation of structural elements under stress. Continuous monitoring of strain can provide insights into load-bearing capacities and help in understanding how structures respond to environmental changes. 3. Temperature. Temperature sensors are essential for assessing thermal expansion and contraction in materials. Fluctuations in temperature can affect the integrity of structures, making temperature monitoring a key aspect of SHM. The integration of these sensors into an IoT framework allows for real-time data transmission to centralized monitoring systems. This connectivity enables engineers to make informed decisions quickly and implement necessary maintenance or repairs. Vibration, strain, and temperature sensing. Vibration sensors, often in the form of accelerometers, are used to detect changes in the vibrational characteristics of structures. By continuously monitoring vibrations, these sensors can identify natural frequencies. Every structure has natural frequencies that can change as it ages or if it experiences damage. Monitoring these frequencies helps in assessing the health of the structure. Dynamic responses. External forces, for example, wind, traffic loads, can cause dynamic responses in a structure. Analyzing these responses can indicate potential weaknesses. Strain sensing. Strain gauges are used to monitor the deformation of structural components. Key aspects include load monitoring. Strain sensors can measure how much load a structure is carrying, which is vital for ensuring safety. Fatigue analysis. Over time, repeated loading can lead to material fatigue. Continuous strain monitoring can help identify areas at risk of failure. Temperature sensing. Temperature sensors, such as thermocouples or infrared sensors, are vital for understanding how temperature variations affect structural integrity. Important factors include thermal expansion. Materials expand and contract with temperature changes. Monitoring these changes helps predict potential structural issues. Environmental impact. Temperature data can be correlated with other environmental factors, humidity, rainfall, to provide a comprehensive assessment of structural health. Case studies of IoT in bridges, tunnels, and high-rise buildings. Case Study 1, IoT in bridges. One prominent example of IoT applications in SHM is the monitoring of the Golden Gate Bridge in San Francisco. The bridge is equipped with a network of sensors that monitor vibration, strain, and temperature. By analyzing the data in real time, engineers can assess the structural health of the bridge and make data-driven maintenance decisions. The sensors also help in understanding how the bridge responds to heavy traffic and environmental factors such as wind and seismic activity. Case Study 2, IoT in tunnels in Europe. The Gotthard Base Tunnel in Switzerland, the world's longest railway and deepest traffic tunnel, utilizes IoT technology for structural health monitoring. Sensors embedded within the tunnel walls monitor strain and temperature, allowing engineers to detect potential issues early. The real-time data collected is crucial for ensuring the safety of the tunnel, especially given the high traffic volume and geological challenges in the region. Case Study 3, IoT in high-rise buildings. The Burj Khalifa in Dubai employs a sophisticated SHM system that integrates IoT sensors to monitor various structural parameters. The system collects data on wind-induced vibrations, temperature fluctuations, and structural strain. This data is analyzed to ensure the safety and longevity of the building, particularly in response to extreme weather conditions. The insights gained from this monitoring system help in optimizing maintenance schedules and ensuring occupant safety. Conclusion: the integration of IoT technologies in structural health monitoring represents a significant advancement in infrastructure management. By utilizing sensors to monitor vibration, strain, and temperature in real time, engineers can ensure the safety and integrity of critical structures. The case studies presented in this chapter illustrate the practical applications of these technologies in bridges, tunnels, and high-rise buildings, highlighting their potential to transform infrastructure maintenance and management. As IoT technology continues to evolve, its impact on structural health monitoring is expected to grow, further enhancing the resilience and safety of our built environment. Chapter 5, Environmental Monitoring. Environmental monitoring is a critical component of sustainable development and disaster management. This chapter explores various technologies and systems that help track environmental conditions, assess risks, and inform decision-making processes. We will delve into air quality, temperature, and humidity sensors, flood and landslide detection systems, and their integration with weather forecasting and disaster management efforts. 5.1 Air quality, temperature, and humidity sensors. Air quality sensors are pivotal in measuring pollutants such as particulate matter, PM2.5 and PM10, nitrogen dioxide, NO2, sulfur dioxide, SO2, carbon monoxide, CO, and ozone, O3. These sensors provide real-time data about the air we breathe and help identify pollution hotspots. Key components, sensor types: electrochemical sensors for gases, optical sensors for particulate matter, temperature and humidity sensors. These are often integrated with air quality sensors to provide a comprehensive view of environmental conditions. High humidity levels can exacerbate the effects of air pollution, while temperature fluctuations can influence pollutant dispersion. Applications: urban planning and management, public health advisories, compliance with environmental regulations. Challenges: sensor calibration and accuracy, data integration from multiple sources. 5.2 Flood and landslide detection systems. Flood and landslide detection systems utilize a range of technologies to monitor environmental changes and predict natural disasters. These systems often incorporate hydrological data, soil moisture levels, and real-time weather information. Key technologies: remote sensing, satellite imagery and aerial drones are used to assess terrain changes and water levels. Ground sensors, in situ sensors measure soil moisture, rainfall, and river levels. Advanced systems can detect ground movement indicative of landslides. Early warning systems. These systems employ algorithms to analyze data and issue alerts before a disaster occurs. For example, changes in soil saturation can trigger warnings for potential landslides. Integration with community response. Local authorities can use data from these systems to prepare emergency response plans, ensuring timely evacuations and resource allocation. 5.3 Integration with weather forecasting and disaster management. The integration of environmental monitoring systems with weather forecasting enhances the ability to predict and respond to disasters. By combining real-time data from sensors with predictive models, authorities can develop more accurate forecasts. Components of integration: data fusion, merging data from various sources, satellite, ground sensors, meteorological stations, to create comprehensive situational awareness. Predictive analytics, utilizing machine learning and statistical methods to predict environmental conditions and potential disasters. Disaster management framework, preparedness. Data informs risk assessments and helps develop evacuation routes and emergency plans. Response: real-time data allows for immediate action during disasters, such as deploying emergency services and communicating with the public. Recovery: post-disaster analysis using collected data can improve future monitoring and response strategies. Case studies: examples of successful integration can be drawn from countries that have effectively used environmental monitoring to mitigate the impacts of floods and landslides. Conclusion: environmental monitoring plays an essential role in understanding and managing the impacts of climate change, urbanization, and natural disasters. By leveraging advanced sensors and integrating data with weather forecasting and disaster management frameworks, communities can become more resilient to environmental challenges. The continuous development of these technologies will enhance our capacity to protect public health, safeguard infrastructure, and support sustainable environmental practices. Chapter 6: Transportation Infrastructure Monitoring. Smart roads and traffic management systems. The evolution of transportation infrastructure is increasingly intertwined with advancements in technology, particularly through the implementation of smart roads and integrated traffic management systems. Smart roads utilize sensors, cameras, and communication technologies to gather real-time data regarding traffic conditions, weather patterns, and road usage. This data enables traffic management systems to optimize signal timings, reduce congestion, and improve overall traffic flow. For example, adaptive traffic signal control systems can adjust signal phases based on current traffic conditions, minimizing wait times and enhancing safety for both vehicles and pedestrians. Furthermore, smart roads can incorporate features such as dynamic lane management, allowing for the reallocation of lanes based on real-time traffic demands. This is particularly useful in urban areas where traffic patterns can fluctuate significantly throughout the day. In addition to improving traffic flow, smart roads can enhance safety through the deployment of connected technologies. For instance, vehicles equipped with vehicle-to-infrastructure (V2I) communication systems can receive alerts about road hazards, construction zones, or traffic incidents, enabling drivers to make informed decisions and reduce the likelihood of accidents. IoT in railway and airport infrastructure. The Internet of Things (IoT) has made significant inroads into railway and airport infrastructure, revolutionizing the way these systems operate and are monitored. In the railway sector, IoT devices are used to monitor the condition of tracks, trains, and signaling systems in real time. Sensors can detect issues such as track degradation, equipment malfunctions, or irregularities in train operation, allowing for proactive maintenance and minimizing service disruptions. Airports are also leveraging IoT technology to enhance operational efficiency and passenger experience. IoT-enabled baggage tracking systems provide real-time updates to travelers about their luggage, reducing anxiety and improving customer satisfaction. Additionally, smart sensors can monitor passenger flow through security and boarding processes, helping airport personnel manage crowd levels and maintain safety protocols. Both sectors benefit from data analytics, which allows for predictive maintenance and operational optimization. By analyzing data collected from various sensors, railway and airport operators can make informed decisions about resource allocation, scheduling, and infrastructure upgrades, ultimately leading to enhanced reliability and service quality. Vehicle to infrastructure, V2I, communication vehicle to infrastructure, V2I. Communication is a critical component of modern transportation systems, enabling vehicles to communicate with infrastructure elements such as traffic signals, road signs, and other roadside devices. This communication enhances road safety, improves traffic efficiency, and supports the development of autonomous vehicle systems. Through V2I communication, vehicles can receive information about traffic conditions, speed limits, and potential hazards ahead. For example, if a vehicle approaches a traffic signal that is about to turn red, the system can provide a warning to the driver or even automatically adjust the vehicle's speed to avoid running the red light. This capability not only promotes safer driving practices but also facilitates smoother traffic flow by reducing abrupt stops and starts. Moreover, V2I communication plays a vital role in the integration of connected and autonomous vehicles into existing transportation networks. As more vehicles become equipped with V2I technology, the ability to share information with infrastructure will enable more coordinated and efficient transportation systems. This synchronization can lead to reduced congestion, lower emissions, and improved travel times for all road users. In conclusion, the integration of smart roads, IoT technologies in railway and airport infrastructure, and V2I communication represents a significant advancement in transportation infrastructure monitoring. These technologies not only improve operational efficiency and safety but also pave the way for more sustainable and user-friendly transportation systems in the future. The ongoing evolution of these systems will require continued investment, collaboration, and innovation to fully realize their potential benefits. Chapter 7: Utility Infrastructure Monitoring. In an era characterized by rapid technological advancements and increasing urbanization, the importance of effective utility infrastructure monitoring cannot be overstated. This chapter delves into the innovative approaches and technologies employed in monitoring water, wastewater, energy, and gas and oil pipeline systems. By leveraging the Internet of Things, IoT, utilities can enhance efficiency, reduce operational costs, and improve service reliability for consumers. Smart water and wastewater management. Water is a precious resource, and its effective management is crucial for sustainability and public health. Smart water management systems utilize IoT sensors and advanced data analytics to monitor water distribution networks, detect leaks, and optimize water usage. Key components: IoT sensors, deployed throughout the water distribution network. These devices collect real-time data on flow rates, pressure, and water quality. Data analytics. Advanced algorithms process the data to identify anomalies, predict potential leaks, and assess water quality in real time. Automated controls. Smart valves and pumps can be adjusted automatically based on data insights, ensuring optimal water flow and pressure. Benefits. Leak detection. Immediate detection of leaks minimizes water loss and reduces the cost of repairs. Water quality monitoring. Continuous monitoring ensures compliance with health standards, providing safe drinking water to communities. Operational efficiency. Data-driven insights help utilities optimize their operations, leading to reduced costs and improved service delivery. IoT in energy grids and power distribution. The integration of IoT technologies into energy grids and power distribution systems has revolutionized the way electricity is generated, distributed, and consumed. Smart grids enable utilities to collect and analyze data from various sources, enhancing grid reliability and efficiency. Key components. Smart meters. These devices track energy consumption in real time, providing consumers with detailed usage data and enabling demand response strategies. Grid sensors. Deployed across the power grid, these sensors monitor voltage levels, power quality, and equipment health. Advanced analytics. Machine learning algorithms analyze data to predict demand, identify outages, and optimize energy distribution. Benefits. Enhanced reliability. Real-time monitoring allows for rapid response to outages and equipment failures, improving overall grid reliability. Energy efficiency. Data insights enable utilities and consumers to manage energy use more effectively, reducing waste and lowering costs. Integration of renewables. Smart grids facilitate the integration of renewable energy sources, enabling a more sustainable energy landscape. Gas and oil pipeline monitoring. The safe transport of gas and oil is critical for energy security and environmental protection. Advanced monitoring technologies are employed to ensure the integrity of pipelines and prevent leaks or spills. Key components. Leak detection systems. Utilizing a combination of sensors and analytics, these systems detect changes in pressure and flow that may indicate a leak. Pipeline surveillance. Drones and satellite imagery are used to monitor pipeline routes for signs of damage or environmental impact. Predictive maintenance. Data analytics are used to anticipate equipment failures and schedule maintenance before issues arise. Benefits. Safety. Early detection of leaks minimizes environmental impact and enhances public safety. Regulatory compliance. Continuous monitoring helps companies comply with environmental regulations and maintain operational licenses. Cost savings. Predictive maintenance reduces the likelihood of costly repairs and downtime, improving overall operational efficiency. Conclusion. The implementation of IoT technologies in utility infrastructure monitoring is transforming the way essential services are managed and delivered. By leveraging real-time data and advanced analytics, utilities can enhance their operational efficiency, ensure public safety, and promote sustainability. As these technologies continue to evolve, the potential for further improvements in utility management and infrastructure resilience is significant, paving the way for smarter cities and a more sustainable future. Chapter 8: Predictive Maintenance Using IoT. The integration of the Internet of Things, IoT, into infrastructure maintenance has transformed traditional maintenance strategies into more proactive and efficient systems. Predictive maintenance, PDM, leverages real-time data collection and advanced analytics to predict when equipment failure might occur, allowing for timely interventions and minimizing downtime. This chapter explores data-driven approaches to maintenance scheduling, the role of machine learning and AI in predictive analytics, and presents case studies that illustrate the successful application of IoT in preventive maintenance. Data-driven approaches to maintenance scheduling. Data-driven maintenance scheduling relies on the continuous collection and analysis of data from various sensors and devices embedded in infrastructure systems. By gathering information on equipment performance, environmental conditions, and usage patterns, organizations can create a dynamic maintenance schedule that adapts to changing conditions rather than relying solely on fixed time intervals or usage metrics. 1. Real-time monitoring. IoT sensors can monitor parameters such as temperature, vibration, and pressure in real time, providing a continuous stream of data that helps identify anomalies indicative of potential failures. 2. Data analytics. Advanced analytics platforms process the collected data to identify trends and patterns. By analyzing historical maintenance records alongside real-time data, organizations can predict when equipment is likely to fail based on its operational history and condition. 3. Condition-based maintenance. This approach shifts the focus from scheduled maintenance to condition-based maintenance, where maintenance actions are performed only when certain indicators show signs of decreasing performance or impending failure. 4. Resource optimization. Data-driven maintenance scheduling can lead to better resource allocation by determining the optimal times for maintenance activities, thus reducing unnecessary downtime and extending the lifespan of equipment. Machine learning and AI for predictive analytics. Machine learning, ML, and artificial intelligence, AI, play crucial roles in enhancing predictive maintenance capabilities. These technologies analyze vast amounts of data to identify complex patterns that would be difficult for humans to discern. 1. Predictive models. ML algorithms can be trained on historical data to develop models that predict future equipment failures. These models can improve over time as more data is collected, leading to increasingly accurate predictions. 2. Anomaly detection. AI techniques can be employed to detect anomalies in real-time operational data. By recognizing unusual patterns, organizations can take corrective actions before minor issues escalate into significant failures. 3. Maintenance decision support. AI can assist maintenance teams by providing recommendations on the best course of action based on predictive analytics. This could include scheduling maintenance, ordering spare parts, or reallocating resources. 4. Integration with other technologies. IoT data combined with AI can be integrated with other systems, such as enterprise resource planning, ERP, and asset management software, to create a holistic view of maintenance needs across an organization. Case studies of IoT in preventive maintenance. Real-world applications of IoT in predictive maintenance demonstrate its effectiveness in various industries. Here are a few notable case studies. 1. Case study 1. Transportation infrastructure. A major city implemented an IoT-based predictive maintenance system for its public transportation fleet. By equipping buses with sensors that monitored engine performance, fuel efficiency, and driver behavior, the city was able to predict maintenance needs before breakdowns occurred. This led to a 30% decrease in maintenance costs and improved service reliability. 2. Case study 2. Manufacturing industry. A manufacturing company integrated IoT sensors into its production lines to monitor machinery health. By applying machine learning algorithms to the collected data, the company could predict equipment failures and schedule maintenance during off-peak hours. This proactive approach reduced unplanned downtime by 40% and increased overall productivity. 3. Case study 3. Utility sector. A utility company used IoT devices to monitor the condition of its power grid infrastructure. By analyzing data on transformer temperatures and electrical loads, the company could predict failures and schedule maintenance before outages occurred. This initiative improved grid reliability and reduced maintenance costs by 25%. Conclusion: predictive maintenance powered by IoT represents a significant advancement in infrastructure maintenance practices. By harnessing data-driven approaches, machine learning, and AI, organizations can optimize maintenance schedules, improve equipment reliability, and reduce operational costs. The case studies highlighted in this chapter reinforce the potential of IoT technologies to transform maintenance strategies across various sectors, leading to enhanced efficiency and performance in infrastructure management. As the technology continues to evolve, the future of predictive maintenance holds promise for even greater advancements in operational excellence. Chapter 9: Remote Monitoring and Control in the Age of Digital Transformation. Remote monitoring and control have become essential for various industries, enabling organizations to optimize operations, enhance productivity, and improve safety. This chapter explores three critical components of remote monitoring and control: real-time data collection and analysis, remote diagnostics and troubleshooting, and automated maintenance systems. 9.1 Real-time data collection and analysis. 9.1.1 Overview: real-time data collection involves gathering information as it occurs, providing immediate insights into system performance. This capability is facilitated by sensors, IoT devices, and advanced communication technologies. The analysis of this data allows organizations to make informed decisions quickly. 9.1.2 Technologies and tools. IoT sensors, devices that monitor temperature, humidity, pressure, and other variables. Cloud computing enables storage and processing of massive datasets from multiple sources. Data analytics software, tools such as machine learning algorithms and statistical models that analyze collected data to identify trends and anomalies. 9.1.3 Applications. Manufacturing, monitoring machinery performance to minimize downtime. Healthcare, tracking patient vitals remotely for timely interventions. Energy management, analyzing consumption patterns to optimize resource allocation. 9.1.4 Benefits, improved decision-making based on real-time insights. Enhanced operational efficiency through proactive monitoring. Greater ability to respond quickly to unforeseen events. 9.2 Remote diagnostics and troubleshooting. 9.2.1 Overview: remote diagnostics and troubleshooting allow technicians and engineers to identify and resolve issues without being physically present at the site. This capability is critical in reducing downtime and minimizing operational disruptions. 9.2.2 Technologies and tools. Remote desktop software enables technicians to access and control systems remotely. Diagnostic tools, software that runs tests and analyzes system performance remotely. Augmented reality, provides technicians with visual aids and overlays to assist in diagnostics. 9.2.3 Applications, IT support, resolving software issues for employees working from various locations. Industrial equipment, diagnosing faults in machinery with minimal site visits. Telemedicine, allowing healthcare providers to assess and diagnose patients remotely. 9.2.4 Benefits, significant reduction in response time to issues. Decreased operational costs by limiting the need for on-site visits. Enhanced customer satisfaction through faster service. 9.3 Automated maintenance systems. 9.3.1 Overview: automated maintenance systems leverage technology to schedule and perform maintenance tasks without human intervention. These systems can predict when maintenance is needed based on real-time data, ensuring that equipment operates smoothly and efficiently. 9.3.2 Technologies and Tools. Predictive maintenance software analyzes data to predict when equipment is likely to fail. Automated scheduling systems organizes and prioritizes maintenance tasks. Robotic process automation (RPA) executes routine maintenance tasks automatically. 9.3.3 Applications. Manufacturing, automating routine checks and repairs on production lines. Transportation, monitoring vehicle conditions and scheduling maintenance to prevent breakdowns. Facilities management, ensuring that building systems, vac, lighting, etc., are maintained without manual oversight. 9.3.4 Benefits. Increased equipment lifespan through timely maintenance. Reduction in maintenance costs due to improved efficiency. Enhanced safety by minimizing the risk of equipment failure. Conclusion. The integration of remote monitoring and control systems is revolutionizing how industries operate. By harnessing real-time data collection and analysis, remote diagnostics and troubleshooting, and automated maintenance systems, organizations can achieve greater operational efficiency, reduce costs, and improve service delivery. As technology continues to advance, the potential for these systems will expand, paving the way for innovative solutions that enhance productivity and safety across sectors. Chapter 10: Asset Management and Tracking. In today's fast-paced and ever-evolving business environment, effective asset management and tracking have become essential for organizations aiming to optimize their operations and enhance their decision-making processes. This chapter delves into various technologies and methodologies that facilitate asset management, including the Internet of Things, IoT, RFID, GPS, and life cycle management of infrastructure assets. IoT for inventory and equipment tracking. The Internet of Things, IoT, has transformed how organizations manage and track their inventory and equipment. By integrating IoT devices, businesses can achieve real-time monitoring of assets, leading to improved efficiency, reduced costs, and enhanced customer satisfaction. Key components of IoT for asset management: sensors and devices. IoT-enabled sensors can track various metrics, including location, temperature, humidity, and usage patterns. These sensors provide invaluable data that can be analyzed for optimal asset utilization. Connectivity. Devices are connected to the Internet, allowing for seamless data transmission. This connectivity enables real-time tracking and monitoring of assets from anywhere in the world. Data analytics. Advanced analytics tools process the data collected from IoT devices, providing insights into asset performance and trends. Organizations can leverage this data for predictive maintenance, inventory optimization, and improved decision-making. Benefits of IoT in asset management: real-time visibility. With IoT, organizations gain real-time visibility into their assets, allowing for immediate response to issues and better inventory control. Enhanced efficiency. Automated tracking reduces manual errors and streamlines operations, leading to increased productivity. Cost savings. By optimizing asset usage and maintenance schedules, organizations can significantly reduce operational costs. RFID and GPS-based asset monitoring. Radio frequency identification, RFID, and global positioning system, GPS, technologies are pivotal in modern asset tracking solutions. These technologies enable businesses to monitor their assets with high accuracy and efficiency. RFID technology. RFID uses electromagnetic fields to automatically identify and track tags attached to objects. Each tag contains a unique identifier that can be read by RFID readers. Advantages of RFID: speed and accuracy. RFID enables rapid scanning of multiple items simultaneously, significantly speeding up inventory processes. Non-line of sight reading. Unlike barcodes, RFID does not require line of sight for scanning, allowing for greater flexibility in asset tracking. Durability. RFID tags are often more durable than traditional labels, making them suitable for harsh environments. GPS technology. GPS is used to determine the precise location of assets in real time. This is particularly beneficial for tracking vehicles, shipping containers, and high-value equipment. Advantages of GPS. Geofencing. Organizations can create virtual boundaries to receive alerts when assets enter or exit designated areas, enhancing security and loss prevention. Route optimization. GPS tracking can help optimize delivery routes, reducing fuel costs and improving service times. Life cycle management of infrastructure assets. Life cycle management of infrastructure assets involves overseeing the entire lifespan of an asset, from planning and acquisition to operation and eventual disposal. Effective life cycle management ensures that assets are utilized efficiently, maintained properly, and replaced or retired at the right time. Phases of asset life cycle management. 1. Planning and acquisition involves assessing needs, budgeting, and procuring assets that align with organizational goals. 2. Operation and maintenance focuses on the day-to-day management of assets, including regular maintenance and performance monitoring to ensure reliability and safety. 3. Performance evaluation. Regular assessments of asset performance help identify areas for improvement and inform decision-making regarding repairs or upgrades. 4. Disposal and replacement. When assets reach the end of their useful life, organizations must evaluate their disposal options, including recycling, resale, or safe disposal. Benefits of effective life cycle management. Maximized asset value. Proper management throughout the asset life cycle helps maximize the return on investment and minimize total ownership costs. Risk mitigation. By anticipating and addressing potential issues before they escalate, organizations can mitigate risks associated with asset failure or obsolescence. Sustainability. Life cycle management promotes sustainable practices by encouraging the responsible use and disposal of assets, aligning with corporate social responsibility goals. Conclusion. As organizations continue to navigate the complexities of asset management, leveraging technologies such as IoT, RFID, and GPS, along with effective life cycle management practices, will be critical. These tools not only enhance operational efficiency and reduce costs but also provide valuable insights that can drive strategic decision-making. By adopting a comprehensive approach to asset management and tracking, businesses can position themselves for long-term success in an increasingly competitive landscape. Chapter 11. Robotics and drones in maintenance. The rapid advancement of technology has significantly transformed maintenance practices across various industries. Two of the most notable innovations are robotics and drones, which have become essential tools for enhancing efficiency, safety, and accuracy in maintenance operations. This chapter delves into the applications of IoT-enabled drones for inspection, robotic systems for repair and maintenance, and the integration of these technologies with IoT platforms. IoT-enabled drones for inspection overview. IoT-enabled drones are unmanned aerial vehicles equipped with sensors and connected to the Internet, allowing for real-time data collection and analysis. These drones are increasingly used in maintenance inspections across sectors such as construction, agriculture, energy, and infrastructure. Applications. 1. Infrastructure inspection. Drones can inspect bridges, power lines, and buildings for structural integrity. Equipped with high-resolution cameras and thermal imaging sensors, they can identify potential issues such as cracks, leaks, and heat anomalies without the need for scaffolding or ladders. 2. Agricultural monitoring. In precision agriculture, drones equipped with multispectral sensors gather data on crop health, soil conditions, and irrigation needs. This information helps farmers to make informed decisions about maintenance and resource allocation. 3. Energy sector surveillance. Drones are deployed to inspect wind turbines, solar panels, and oil rigs, reducing the risk to human inspectors and allowing for more frequent and comprehensive assessments. Benefits. Cost efficiency. Drones reduce the need for manual inspections that are often time-consuming and labor-intensive. Safety. By using drones, maintenance teams can avoid hazardous environments and reduce the risk of accidents. Data accuracy. IoT-enabled drones provide high-quality data that can be analyzed to predict maintenance needs and extend asset lifespan. Robotic systems for repair and maintenance overview. Robotic systems are increasingly used in various maintenance tasks, from performing routine repairs to complex troubleshooting. These robots can operate in environments that are dangerous or difficult for human workers. Applications. 1. Manufacturing maintenance robots. In manufacturing settings, robots are used for predictive maintenance on machinery, utilizing sensors to monitor equipment health and perform repairs autonomously. 2. Automated cleaning systems. Robots are deployed in facilities such as airports and hospitals to maintain cleanliness. These systems can navigate spaces autonomously, ensuring that maintenance tasks are performed consistently. 3. Telepresence robots. In remote locations, telepresence robots allow maintenance experts to conduct repairs and inspections from afar, providing guidance and oversight while the robot performs tasks on site. Benefits. Increased productivity. Robotics can operate continuously without fatigue, leading to higher output levels. Precision and consistency. Robots can perform tasks with a level of precision that exceeds human capabilities, ensuring high-quality maintenance work. Adaptability. Robotic systems can be programmed or trained to handle various maintenance tasks, allowing for flexibility in operations. Integration with IoT platforms. Overview. The integration of drones and robotic systems with IoT platforms enhances their capabilities by enabling seamless data communication, real-time monitoring, and advanced analytics. Applications. 1. Data aggregation. IoT platforms collect data from drones and robots, providing a centralized system for monitoring equipment health and maintenance status across multiple assets. 2. Predictive analytics. By analyzing data collected from inspections and maintenance activities, IoT platforms can predict failures before they occur, allowing for proactive maintenance strategies. 3. Remote monitoring and control. Maintenance teams can monitor the status and performance of drones and robots remotely, enabling quick response to issues and more efficient resource allocation. Benefits. Enhanced decision-making. The integration of IoT data allows organizations to make informed decisions regarding maintenance schedules and resource management. Improved asset management. Companies can track the performance and condition of their assets in real time, optimizing maintenance efforts and reducing downtime. Scalability. As organizations grow, integrating drones and robots with IoT platforms allows for easy scaling of maintenance operations to accommodate new assets. Conclusion. The integration of robotics and drones into maintenance practices represents a significant leap forward in efficiency, safety, and data-driven decision-making. IoT-enabled drones enhance inspection capabilities, while robotic systems improve repair and maintenance tasks. By leveraging IoT platforms, organizations can create a cohesive maintenance strategy that optimizes asset management and minimizes operational risks. As technology continues to evolve, the synergy between robotics, drones, and IoT will pave the way for innovative maintenance solutions across industries. Chapter 12: Big Data in Infrastructure Monitoring. Data collection, storage, and processing. Data collection in the context of infrastructure monitoring. Data collection refers to the systematic gathering of information from various sources, often through Internet of Things, IoT, devices. These devices can include sensors, cameras, and other monitoring equipment that track parameters such as temperature, humidity, structural integrity, and traffic patterns. IoT devices enable real-time data collection, which is crucial for proactive infrastructure management. The data collected can be structured, like numerical data from sensors, or unstructured, like video feeds from cameras. Technologies such as edge computing can facilitate immediate processing of data at the source, reducing latency and bandwidth usage. Data storage. Once collected, data must be stored efficiently to support subsequent analysis. Traditional databases may struggle with the volume, velocity, and variety of big data. As a result, organizations often turn to distributed storage solutions, such as NoSQL databases. Databases like MongoDB and Cassandra provide flexibility in handling unstructured data and scalability to accommodate growing data volumes. Data lakes. These repositories allow organizations to store raw data in its native format for later processing and analysis. Technologies like Apache Hadoop and Amazon S3 are commonly used for creating data lakes. Cloud storage solutions. Cloud platforms offer scalable storage options that can dynamically adjust to the needs of the monitoring system. Data processing. Processing large-scale IoT data involves transforming raw data into a usable format for analysis. This can include batch processing, suitable for processing large volumes of data at once, often using frameworks like Apache Hadoop or Apache Spark. Stream processing, ideal for real-time data processing, where tools like Apache Kafka and Apache Flink are employed to analyze data as it arrives. Effective data processing ensures that organizations can derive actionable insights from the data, enabling timely decision-making regarding infrastructure maintenance and improvements. Challenges of handling large-scale IoT data. Handling large-scale IoT data presents several challenges. 1. Data volume. The sheer volume of data generated by IoT devices can be overwhelming. Infrastructure monitoring systems may produce terabytes or petabytes of data daily, requiring robust systems for storage and processing. 2. Data velocity. Data velocity refers to the speed at which data is generated and needs to be processed. Real-time analytics are essential for timely decision-making in infrastructure monitoring, but achieving this can be challenging due to the high data throughput. 3. Data variety. IoT data comes in various formats, including structured, semi-structured, and unstructured data. Managing this diversity requires flexible data processing and storage solutions that can accommodate different data types. 4. Data quality. Ensuring data accuracy and reliability is crucial for effective monitoring. Inaccurate or noisy data can lead to incorrect conclusions and poor decision-making. Implementing data validation and cleansing processes is essential. 5. Security and privacy. IoT devices are often vulnerable to cyber threats. Protecting sensitive infrastructure data is critical, requiring robust security measures such as encryption, access controls, and regular security audits. 6. Integration with existing systems. Integrating new big data solutions with legacy systems can pose technical challenges. Organizations must ensure compatibility and consider the impact on existing workflows. Data visualization and reporting tools. Effective data visualization and reporting tools are essential for translating complex data into actionable insights. These tools help stakeholders understand trends, patterns, and anomalies in infrastructure performance. Visualization tools, dashboards, platforms like Tableau, Power BI, and Grafana allow users to create interactive dashboards that display real-time data visualizations. These dashboards can provide insights into key performance indicators, KPIs, for infrastructure monitoring. Geospatial visualization. Tools like ArcGIS and Google Maps enable the visual representation of data in a geographic context, which is particularly useful for monitoring infrastructure spread across large areas. Reporting tools. Automated reporting. Tools that generate automated reports can save time and ensure that stakeholders receive regular updates on infrastructure status. These reports can include visualizations and summaries of critical metrics. Custom reporting. Organizations may need to create custom reports tailored to specific needs, using tools like Crystal reports or for more advanced statistical reporting. Importance of user-friendly interfaces. User-friendly interfaces are crucial for ensuring that non-technical stakeholders can easily interpret data visualizations and reports. Intuitive designs can facilitate better decision-making and foster collaboration across teams. Conclusion. Big data plays a transformative role in infrastructure monitoring, enabling organizations to collect, store, and analyze vast amounts of data from IoT devices. By addressing challenges related to data volume, velocity, variety, quality, security, and integration, organizations can leverage data analytics to enhance decision-making and improve infrastructure management. Effective visualization and reporting tools further empower stakeholders to make informed choices based on real-time data insights. Chapter 13: AI and Machine Learning for Smart Infrastructure. In the era of rapid technological advancement, the integration of artificial intelligence, AI, and machine learning, ML, into infrastructure management has become essential for enhancing efficiency, ensuring safety, and prolonging the lifespan of critical assets. This chapter delves into three key areas where AI and ML are revolutionizing smart infrastructure: predictive modeling for infrastructure health, anomaly detection and fault diagnosis, and the optimization of maintenance strategies. Predictive modeling for infrastructure health. Predictive modeling leverages historical data and machine learning algorithms to forecast the future condition of infrastructure components. This approach enables asset managers to transition from reactive maintenance strategies to proactive measures, significantly reducing downtime and maintenance costs. 1.1 Data collection and pre-processing. Data collection is the foundation of predictive modeling. For infrastructure health, data can be gathered from various sources, including sensors, IoT devices deployed across infrastructure, for example, bridges, roads, pipelines, that monitor conditions such as strain, temperature, and vibration. Inspection reports. Regular assessments conducted by engineers that provide qualitative and quantitative insights into the state of assets. Historical maintenance records. Data on past repairs and maintenance activities that can help identify patterns and trends. Once collected, data pre-processing is crucial for ensuring quality and relevance. This step may include cleaning, normalization, and feature extraction to enhance model performance. 1.2 Model development. Various machine learning techniques can be employed for predictive modeling, including regression analysis, used to predict continuous outcomes, such as the remaining useful life, RUL, of a component. Classification algorithms, employed to categorize infrastructure conditions into different risk levels, for example, good, fair, poor. Time series forecasting, essential for predicting future conditions based on historical time-dependent data. 1.3 Implementation and outcomes. The implementation of predictive models allows infrastructure operators to schedule maintenance activities based on predicted failures, allocate resources more efficiently by focusing on high-risk assets, improve overall asset management and decision-making processes. Anomaly detection and fault diagnosis. Anomaly detection refers to the identification of unusual patterns or behaviors in data that may indicate potential failures or issues within infrastructure systems. ML techniques play a crucial role in automating this process, enabling real-time monitoring and rapid response. 2.1 Techniques for anomaly detection. Several ML methods can be utilized for anomaly detection, including statistical methods, simple threshold-based approaches that identify outliers based on historical data averages, machine learning models, algorithms like isolation forest, one-class SVM, and autoencoders that can learn normal operational patterns and flag deviations. Deep learning, neural networks that can analyze complex data structures and detect subtle anomalies, particularly in high-dimensional data. 2.2 Fault diagnosis. Once anomalies are detected, diagnosing the underlying causes is crucial for effective remediation. Techniques include causal analysis, using ML to identify correlations and possible causative factors of anomalies. Root cause analysis, applying techniques such as decision trees or random forests to trace back through the data and identify the fundamental issues leading to failures. 2.3 Benefits of anomaly detection and diagnosis. Implementing these techniques provides several advantages: early identification of potential failures, thereby reducing the risk of catastrophic events. Enhanced safety and reliability of infrastructure systems. Improved operational efficiency through timely interventions. Optimization of maintenance strategies. Optimizing maintenance strategies is vital for minimizing costs while maximizing asset performance and lifespan. AI and ML can significantly enhance decision-making in this area. 3.1 Maintenance strategy framework. The optimization process typically involves predictive maintenance, utilizing predictive models to forecast when maintenance should occur, rather than adhering to fixed schedules. Condition-based maintenance, performing maintenance based on the actual condition of assets as indicated by real-time data. 3.2 Reinforcement learning for maintenance optimization. Reinforcement learning, RL, can be particularly effective in optimizing maintenance strategies. RL algorithms learn to make decisions based on receiving feedback from their actions, allowing them to identify the most effective maintenance interventions over time. 3.3 Cost-benefit analysis. RL-driven optimization strategies can lead to significant cost savings through reduced downtime, minimizing unplanned outages and extending the life of infrastructure components. Resource efficiency, optimizing labor and material allocation based on predictive insights. Conclusion. The integration of AI and machine learning into smart infrastructure management is transforming the way we monitor, maintain, and optimize critical assets. By leveraging predictive modeling, anomaly detection, and optimized maintenance strategies, infrastructure operators can enhance safety, reduce costs, and ensure the reliability of systems that are vital to modern society. As technology continues to evolve, the potential for these applications will only grow, paving the way for smarter, more resilient infrastructure systems. Chapter 14: Cybersecurity in IoT-enabled infrastructure. The integration of Internet of Things, IoT, devices into infrastructure has transformed various sectors, including smart cities, healthcare, transportation, and industrial automation. However, this transformation has also introduced a myriad of cybersecurity challenges. This chapter delves into the threats and vulnerabilities inherent in IoT systems, outlines best practices for securing IoT networks, and discusses regulatory and compliance considerations that organizations must navigate. Threats and vulnerabilities in IoT systems. IoT systems are particularly susceptible to a range of cybersecurity threats due to their unique characteristics, such as diverse devices, limited computational power, and often inadequate security measures. The primary threats include: 1. Unauthorized access, weak authentication. Many IoT devices use default or weak passwords, making them easy targets for unauthorized access. Lack of encryption. Data transmitted between devices may not be encrypted, exposing sensitive information to interception. 2. Malware and ransomware. IoT devices can be infected with malware that can hijack functionality or encrypt data for ransom, leading to significant operational disruptions. 3. DoS attacks. Distributed denial of service, DoS, attacks can exploit large networks of compromised IoT devices to overwhelm and disable services. 4. Physical attacks. Devices can be physically tampered with, allowing attackers to gain direct access to the device and its data. 5. Data breaches. Sensitive information collected by IoT devices, such as personal health data or security surveillance footage, can be targeted for theft. 6. Interoperability issues. Diverse devices and protocols can lead to security gaps if not properly integrated, allowing attackers to exploit weaknesses in less secure devices. Best practices for securing IoT networks. To mitigate the risks associated with IoT systems, organizations should implement a comprehensive cybersecurity strategy that incorporates the following best practices. 1. Device authentication and authorization. Implement strong authentication mechanisms, such as multi-factor authentication, MFA, to ensure that only authorized users can access IoT devices. 2. Data encryption. Use encryption protocols for data in transit and at rest to protect sensitive information from interception and unauthorized access. 3. Regular software updates and patch management. Ensure that all IoT devices are regularly updated with the latest firmware and security patches to address vulnerabilities. 4. Network segmentation. Segment IoT devices from critical systems and sensitive data to reduce the attack surface and limit the potential impact of a breach. 5. Monitoring and anomaly detection. Implement continuous monitoring solutions to detect unusual behavior or anomalies in IoT networks, allowing for prompt response to potential threats. 6. Security by design. Integrate security considerations into the design and development phases of IoT devices and applications to ensure robust security features are embedded from the outset. 7. User education and awareness. Train employees and end users on best practices for IoT security, including recognizing phishing attempts and maintaining device security. Regulatory and compliance considerations. As IoT technology continues to evolve, so too do the regulatory and compliance frameworks governing its use. Organizations must be aware of and adhere to relevant regulations, which may vary by region and industry. Key considerations include: 1. Data protection regulations. Compliance with data protection laws such as the General Data Protection Regulation, GDPR, in Europe, the Health Insurance Portability and Accountability Act, HIPAA, in the U.S. healthcare sector, and similar regulations worldwide is crucial for protecting personal data collected by IoT devices. 2. Industry standards. Adherence to industry-specific standards and frameworks, such as the National Institute of Standards and Technology, NIST, Cybersecurity Framework or the Internet Engineering Task Force, IETF, standards, can guide organizations in implementing security best practices. 3. Privacy considerations. Organizations must consider privacy implications when deploying IoT devices, ensuring that data collection practices are transparent and that user consent is obtained where necessary. 4. Liability and accountability. Establish clear policies regarding liability in the event of a data breach or security incident involving IoT devices, clarifying the responsibilities of manufacturers, service providers, and users. 5. Third-party risk management. Evaluate and manage the security practices of third-party vendors and partners who provide IoT devices or services, as their vulnerabilities can impact your organization's security posture. Conclusion. The cybersecurity landscape of IoT-enabled infrastructure is complex and ever-evolving. By understanding the threats and vulnerabilities associated with IoT systems, implementing best practices for securing networks, and adhering to regulatory requirements, organizations can better protect themselves against the risks posed by this technology. As IoT continues to expand, proactive cybersecurity measures will be essential for safeguarding sensitive data and maintaining the integrity of critical infrastructure. Chapter 15: Smart Cities and IoT Infrastructure. IoT in Urban Planning and Development. The integration of the Internet of Things, IoT, into urban planning and development represents a transformative approach to managing city infrastructure, services, and resources. Smart cities leverage IoT technology to enhance the quality of life for residents, improve operational efficiency, and promote sustainable practices. Key components of IoT in urban planning include: 1. Data collection and analysis. IoT devices, such as sensors, cameras, and connected vehicles, collect vast amounts of data related to traffic patterns, energy consumption, waste management, and public safety. This data is essential for informed decision-making and urban planning. 2. Smart infrastructure. Infrastructure such as smart street lights, traffic signals, and waste bins equipped with sensors can optimize energy use, reduce congestion, and streamline waste collection processes. These systems improve overall city efficiency and reduce costs. 3. Public safety and security. IoT technologies can enhance public safety through surveillance cameras, gunshot detection systems, and emergency response systems that use real-time data to respond more effectively to incidents. 4. Sustainability initiatives. Smart cities often prioritize sustainability by utilizing IoT for monitoring environmental factors, such as air quality and noise pollution, and by promoting energy-efficient buildings and renewable energy sources. 5. Citizen engagement. IoT solutions empower residents to engage with their city through mobile apps and platforms that provide real-time information about public services, transportation, and community events, fostering a sense of community and participation. Case studies of smart city projects. 1. Barcelona, Spain. Barcelona has implemented a comprehensive smart city strategy that utilizes IoT technology across various sectors. Key initiatives include: smart lighting. The city has installed smart street lights that adjust brightness based on pedestrian and vehicle presence, resulting in energy savings and improved safety. Waste management. Smart bins equipped with sensors notify waste collection services when they are full, optimizing collection routes and reducing operational costs. Traffic management. IoT sensors monitor traffic flow and adjust traffic signals in real time to reduce congestion and improve mobility. 2. Songdo. South Korea Songdo is a purpose-built smart city that incorporates IoT technology from its inception. Notable features include integrated transportation system. A comprehensive network of sensors and data analytics allows for efficient public transportation management, including real-time tracking of buses and subways. Green building initiatives. Buildings are designed with sustainability in mind, featuring energy-efficient systems that are connected to a central management system to monitor and optimize resource use. Smart water management. IoT sensors monitor water quality and usage, allowing for proactive management of resources and reducing leaks and waste. 3. Amsterdam, Netherlands. Amsterdam's smart city initiatives focus on sustainability and citizen engagement. Smart energy grids. The city has developed a smart energy grid that allows for the integration of renewable energy sources and encourages energy conservation among residents. Mobility solutions. Through a network of sensors and apps, the city promotes cycling and public transport while reducing car usage, contributing to lower emissions. Open data platform. Amsterdam provides an open data platform that allows citizens and businesses to access city data, fostering innovation and collaboration. Lessons learned and future directions. As cities around the world continue to implement IoT technology, several key lessons have emerged. 1. Interoperability and standards. The importance of establishing common standards and protocols for IoT devices to ensure seamless integration and communication between systems cannot be overstated. 2. Privacy and security. Addressing concerns related to data privacy and cybersecurity is critical. Cities must implement robust security measures to protect sensitive information and maintain public trust. 3. Community involvement. Engaging with residents during the planning and implementation phases of smart city projects is essential to ensure that initiatives meet the needs and expectations of the community. 4. Scalability and flexibility. Smart city solutions should be designed with scalability in mind, allowing cities to adapt and expand their IoT infrastructure as needs evolve. 5. Sustainability as a core principle. Future smart city projects must prioritize sustainability, leveraging IoT technology to create resilient urban environments that can withstand climate challenges. In conclusion, the integration of IoT into urban planning and development is a crucial step towards creating smarter, more sustainable cities. By learning from existing case studies and addressing challenges head-on, cities can harness the full potential of IoT technology to improve the quality of life for their residents and ensure a sustainable future. Chapter 16, IoT in Industrial Infrastructure. The integration of the Internet of Things, IoT, into industrial infrastructure has revolutionized the way factories, plants, and other facilities operate. By enabling real-time monitoring, predictive maintenance, and enhanced operational efficiency, IoT technologies are transforming traditional industries such as manufacturing, oil and gas, and mining. This chapter explores the various applications of IoT in these sectors, highlighting its impact on productivity, safety, and sustainability. Monitoring and maintenance of factories and plants. Real-time data collection. IoT sensors can monitor various parameters within factories and plants, including temperature, humidity, equipment performance, and energy consumption. These sensors collect real-time data, allowing managers to make informed decisions based on current operating conditions. Predictive maintenance. One of the most significant advantages of IoT in industrial settings is predictive maintenance. By analyzing data from machinery, IoT systems can predict when equipment is likely to fail, allowing for timely maintenance before a breakdown occurs. This approach minimizes downtime and reduces maintenance costs, leading to greater operational efficiency. Enhanced safety. IoT technologies also enhance workplace safety by providing real-time alerts regarding hazardous conditions. Wearable devices equipped with sensors can monitor workers' health metrics and environmental factors, ensuring timely interventions in case of emergencies. Additionally, IoT can track equipment usage patterns, helping to identify safety risks associated with machine operation. Energy management. IoT solutions can significantly improve energy efficiency in factories and plants. Smart meters and energy monitoring systems enable organizations to track energy consumption in real time, identify inefficiencies, and implement strategies to reduce energy waste. This not only lowers operational costs but also contributes to sustainability goals. IoT in oil and gas facilities. Asset monitoring and management. In the oil and gas industry, IoT devices are used to monitor assets such as pipelines, drilling rigs, and refineries. Sensors can detect leaks, corrosion, and other potential issues, allowing for rapid response and minimizing environmental risks. Remote monitoring systems enable operators to oversee operations from a distance, enhancing safety and efficiency. Downhole monitoring. IoT applications extend to downhole operations, where sensors provide real-time data on pressure, temperature, and flow rates during drilling and production. This data is crucial for optimizing extraction processes and ensuring the integrity of well operations. Supply chain optimization. The oil and gas sector relies heavily on complex supply chains. IoT technologies can enhance logistics by tracking the movement of materials and products, predicting demand, and optimizing inventory levels. This leads to reduced costs and improved service delivery. Environmental compliance. IoT solutions assist oil and gas companies in meeting regulatory compliance standards. By continuously monitoring emissions and environmental impact, organizations can demonstrate their commitment to sustainability and reduce the risk of penalties associated with non-compliance. Applications in mining and heavy industries. Resource extraction optimization. In mining operations, IoT technology can optimize resource extraction processes. Sensors can monitor equipment performance, track material movement, and assess geological conditions, allowing for more efficient operations and reduced waste. Fleet management. Heavy industries often rely on large fleets of vehicles and machinery. IoT solutions provide real-time tracking of equipment locations, usage patterns, and maintenance needs, enabling better fleet management. This leads to reduced costs, improved asset utilization, and enhanced safety. Worker safety and health. Similar to other industrial sectors, worker safety is a top priority in mining and heavy industries. Wearable IoT devices can monitor workers' physical conditions and environmental factors, providing alerts in case of hazardous situations. This proactive approach to safety helps protect workers in high-risk environments. Environmental monitoring. Mining operations have significant environmental impacts. IoT technologies can monitor air and water quality, noise levels, and other ecological factors, enabling companies to take corrective actions when necessary. By prioritizing sustainability, mining companies can mitigate their environmental footprint and improve community relations. Conclusion. The adoption of IoT technologies in industrial infrastructure is driving a new era of operational efficiency, safety, and sustainability. From real-time monitoring and predictive maintenance in factories to asset management in oil and gas facilities and resource optimization in mining, IoT is reshaping the landscape of traditional industries. As these technologies continue to evolve, they will undoubtedly play a crucial role in the future of industrial infrastructure. Embracing IoT not only enhances productivity but also fosters a culture of innovation and responsibility in managing industrial operations. Chapter 17, IoT in Rural and Remote Infrastructure. The Internet of Things, IoT, has the potential to revolutionize rural and remote infrastructure by enhancing connectivity, increasing efficiency, and improving quality of life. However, deploying IoT solutions in these areas comes with its own set of challenges. This chapter explores the obstacles faced, presents case studies that illustrate successful implementations, and discusses strategies for bridging the digital divide. Challenges of deploying IoT in remote areas. 1. Connectivity limitations. One of the most significant challenges in rural and remote areas is the lack of reliable internet connectivity. Many of these regions suffer from inadequate broadband infrastructure, which can hinder the deployment of IoT devices that rely on constant data transmission. 2. Power supply issues. IoT devices require power to operate, and in remote areas, access to a stable power supply can be problematic. The reliance on batteries can lead to maintenance issues, while solar power solutions may not be viable in all locations due to environmental conditions. 3. Cost constraints. Budget limitations in rural communities can impede the adoption of IoT technologies. Initial setup costs, ongoing maintenance, and the need for skilled personnel can be prohibitive, particularly in areas where financial resources are scarce. 4. Technical expertise. The deployment and maintenance of IoT systems require a certain level of technical expertise that may not be readily available in rural areas. This skills gap can lead to challenges in managing and troubleshooting IoT applications. 5. Data security and privacy. The increased connectivity of IoT devices raises concerns about data security and privacy. Rural areas may lack the necessary cybersecurity infrastructure to protect sensitive information, making them vulnerable to breaches. Case studies of IoT in rural infrastructure. 1. Smart agriculture in India. In India, IoT solutions have been implemented in agriculture to optimize water usage and enhance crop yields. By deploying soil moisture sensors and weather stations, farmers can receive real-time data on irrigation needs, leading to more efficient water management. This not only conserves water but also improves crop productivity, showcasing the benefits of IoT in rural farming. 2. Remote health monitoring in Africa. Telemedicine solutions utilizing IoT devices have been deployed in several African countries to bridge the healthcare gap in remote areas. Wearable health monitors collect vital signs and transmit data to healthcare providers, allowing for timely interventions and reducing the need for patients to travel long distances for care. This case emphasizes how IoT can enhance healthcare accessibility in rural regions. 3. Smart water management in Australia. In Australia, IoT technology has been used to manage water resources more effectively in rural areas. Smart sensors placed in water distribution systems monitor flow rates and detect leaks, enabling faster response times and reducing water wastage. This implementation highlights the potential for IoT to improve essential services in remote communities. Bridging the digital divide. 1. Infrastructure investment. Investing in infrastructure is crucial to improving connectivity in rural and remote areas. Governments and private organizations must collaborate to expand broadband access and ensure that IoT solutions can be effectively deployed. 2. Community engagement. Engaging local communities in the planning and implementation of IoT projects is vital. By involving residents in decision-making processes, solutions can be tailored to meet specific needs and address local challenges. 3. Education and training. To overcome the skills gap, targeted education and training programs should be established. Providing resources and training for local residents will help build the necessary expertise to manage and maintain IoT systems. 4. Innovative financing models. Developing innovative financing models, such as public-private partnerships or microfinancing, can help alleviate the cost barriers associated with deploying IoT solutions in rural areas. These models can provide the necessary capital for initial investments and ongoing maintenance. 5. Policy support. Policymakers must create supportive regulatory environments that encourage the adoption of IoT technologies in rural areas. This includes developing standards for data security, incentivizing investment in infrastructure, and promoting research and development in IoT applications tailored for rural contexts. Conclusion. The deployment of IoT in rural and remote infrastructure presents significant opportunities to enhance quality of life and improve service delivery. However, addressing the inherent challenges is essential for realizing these benefits. By learning from successful case studies and implementing strategies to bridge the digital divide, stakeholders can create a more connected and sustainable future for rural communities. Chapter 18: 5G and Beyond in IoT Infrastructure. The rapid evolution of the Internet of Things, IoT, is significantly influenced by advancements in communication technologies, with 5G at the forefront of this transformation. This chapter explores the role of 5G in enhancing IoT connectivity, the importance of edge computing and decentralized networks, and the potential future communication technologies that could further revolutionize IoT infrastructure. Role of 5G in enhancing IoT connectivity. 5G technology represents a monumental leap in mobile communication, offering unprecedented speed, low latency, and the ability to connect a massive number of devices simultaneously. These attributes are critical for IoT applications that require real-time data transmission and responsiveness. 1. Enhanced data speeds. 5G networks can deliver data rates exceeding 10 Gbps, enabling faster uploads and downloads. This is particularly beneficial for IoT devices that generate large amounts of data, such as video surveillance cameras and high-definition sensors. 2. Ultra-low latency. With latency as low as 1 millisecond, 5G allows for near-instantaneous communication between devices. This is essential for applications requiring real-time interaction, such as autonomous vehicles, remote surgeries, and industrial automation. 3. Massive device connectivity. 5G can support up to 1 million devices per square kilometer, making it ideal for dense IoT environments such as smart cities and industrial IoT ecosystems. This capability ensures that networks can handle the exponential growth of connected devices without compromising performance. 4. Network slicing. 5G introduces the concept of network slicing, where virtual networks can be created on the same physical infrastructure. This allows for tailored connectivity solutions for specific IoT applications, ensuring that critical systems receive the necessary bandwidth and reliability. Edge computing and decentralized networks. As the number of connected devices continues to grow, so does the need for efficient data processing and management. Edge computing emerges as a solution to address these challenges by bringing computation and data storage closer to the source of data generation. 1. Reduced latency and bandwidth use. By processing data at the edge, closer to the devices, edge computing reduces the need to send all data to centralized cloud servers. This minimizes latency and conserves bandwidth, allowing for quicker decision-making and response times. 2. Real-time analytics. Edge devices can perform real-time analytics, enabling immediate insights and actions based on data collected from IoT sensors. This is crucial for applications like predictive maintenance in manufacturing and real-time monitoring in healthcare. 3. Resilience and reliability. Decentralized networks enhance the resilience of IoT systems. In the event of a network outage or failure, edge devices can continue to operate autonomously, ensuring that critical applications remain functional. 4. Enhanced security. By processing data locally, edge computing can reduce the risk of data breaches associated with transferring sensitive information to central servers. Additionally, decentralized networks can implement distributed security measures, making it harder for malicious actors to compromise the system. Future communication technologies. While 5G is currently the benchmark for IoT connectivity, several emerging communication technologies promise to build on its capabilities and drive the next wave of innovation in IoT. 1. 6G technology, expected to roll out in the 2030s. 6G aims to provide even faster data rates, lower latency, and greater reliability. It will leverage advanced technologies such as terahertz communication and AI-driven networks to create a highly interconnected and intelligent IoT ecosystem. 2. Low-power wide-area networks. LPWAN technologies like LoRaWAN and NB-IoT are designed for long-range communication with low power consumption. These networks are ideal for IoT applications requiring long battery life and wide coverage, such as agricultural monitoring and smart metering. 3. Satellite IoT. The integration of satellite communication with IoT networks can enhance connectivity in remote and underserved areas. Emerging satellite constellations aim to provide global coverage, enabling IoT applications in agriculture, maritime, and disaster response. 4. Quantum communication. As quantum technology advances, it promises to revolutionize secure communications. Quantum key distribution, QKD, could provide unprecedented levels of security for IoT devices, protecting sensitive data from potential cyber threats. Conclusion. The interplay between 5G technology, edge computing, and future communication innovations is set to redefine the IoT landscape. As these technologies mature and converge, they will enable more robust, scalable, and secure IoT infrastructures, paving the way for smarter cities, connected industries, and transformative applications that enhance everyday life. The future of IoT is not just about connectivity, it's about creating intelligent ecosystems that can learn, adapt, and respond in real time to the needs of individuals and society as a whole. Chapter 19: Digital Twins for Smart Infrastructure. Concept and applications of digital twins. Digital twins are virtual replicas of physical assets, systems, or processes that allow for real-time monitoring, analysis, and optimization. They serve as a bridge between the physical and digital worlds, enabling organizations to simulate, predict, and enhance the performance of their infrastructure. The concept of a digital twin originated in manufacturing, but its applications have expanded into various sectors, including transportation, energy, healthcare, and urban planning. Key concepts. 1. Definition. A digital twin is a dynamic digital representation of a physical entity, capturing its characteristics and behavior throughout its life cycle. 2. Components. Digital twins consist of 3 main components: physical asset, the actual physical entity being represented; digital model, the virtual representation that simulates the behavior and performance of the physical asset; data connection, the integration of real-time data from sensors and IoT devices that feed information to the digital model. 3. Applications. Predictive maintenance, monitoring equipment health to predict failures before they occur, thereby reducing downtime and maintenance costs. Performance optimization, analyzing data to enhance the performance and efficiency of infrastructure systems, like optimizing traffic flow in smart cities. Design and simulation, testing and improving designs before implementing them in the physical world, which can lead to cost savings and reduced time to market. Integration with IoT for real-time monitoring. The integration of digital twins with the Internet of Things, IoT, is pivotal for enabling real-time monitoring and decision-making. IoT devices, equipped with sensors, collect vast amounts of data from the physical world, which is then transmitted to the digital twin for analysis. Key aspects: 1. Data collection. IoT sensors gather data related to temperature, pressure, humidity, location, and more from physical assets. This data is essential for the digital twin to accurately reflect the current state of the asset. 2. Real-time processing. The digital twin processes incoming data in real time, allowing operators to visualize asset performance and respond to issues as they arise. 3. Feedback loop. The insights gained from the digital twin can inform decisions about maintenance, upgrades, or operational changes in the physical asset, creating a continuous feedback loop that enhances both the digital twin and the physical counterpart. 4. Scalability. The integration of IoT enables scalability, allowing organizations to develop digital twins for multiple assets simultaneously and manage them from a centralized platform. Case studies of digital twin implementations. Case study 1. Smart transportation systems. In a major metropolitan area, a city implemented digital twins to manage its transportation infrastructure. By integrating IoT sensors across the city's roadways, traffic signals, and public transit systems, the digital twin provided real-time insights into traffic patterns, congestion points, and public transport availability. Outcome: the city was able to optimize traffic flow, reduce travel times, and enhance public transport efficiency. Predictive analytics helped city planners understand future traffic trends and make informed decisions about infrastructure investments. Case study 2. Energy management in smart grids. A utility company adopted digital twin technology to monitor and manage its smart grid infrastructure. By creating digital twins of power generation facilities, substations, and distribution networks, the utility could simulate the impacts of various operational scenarios. Outcome: the digital twin allowed for real-time monitoring of energy demand and supply, leading to improved load balancing and reduced energy waste. The company also enhanced its predictive maintenance strategies, resulting in lower operational costs and improved service reliability. Case study 3. Building management systems. In the construction of a smart building, the developers integrated digital twin technology into the building management system. Sensors monitored vac systems, lighting, and occupancy levels, feeding data into the digital twin. Outcome: the digital twin provided insights for optimizing energy usage, improving occupant comfort, and identifying maintenance needs before they became critical. This proactive approach not only reduced operational costs but also enhanced the overall sustainability of the building. Conclusion: digital twins represent a transformative approach to managing smart infrastructure by providing a comprehensive view of physical assets and systems. Their integration with IoT facilitates real-time monitoring, predictive analytics, and performance optimization, paving the way for more efficient, sustainable, and resilient infrastructure. As organizations continue to explore and implement digital twin technologies, the potential applications and benefits will only expand, shaping the future. Chapter 20: Sustainable and Resilient Infrastructure. In the face of climate change and rapid urbanization, the need for sustainable and resilient infrastructure has never been more pressing. This chapter examines the potential of the Internet of Things, IoT, in creating infrastructure that not only withstands environmental challenges but also promotes sustainability. The three focal areas discussed are IoT for climate-resilient infrastructure, energy-efficient IoT solutions, and the role of IoT in achieving the Sustainable Development Goals, SDGs. IoT for climate-resilient infrastructure. Climate change poses significant threats to infrastructure, from extreme weather events to rising sea levels. IoT technologies provide a means to enhance the resilience of infrastructure systems through real-time monitoring, predictive analytics, and automated responses. 1. Real-time monitoring. IoT sensors installed in bridges, roads, and buildings can monitor structural integrity, detect early signs of wear, and identify potential failures before they occur. This proactive approach allows for timely maintenance and upgrades, reducing the risk of catastrophic failures. 2. Data-driven decision-making. By collecting and analyzing vast amounts of data from various sources, such as weather patterns, seismic activity, and traffic flow, urban planners and engineers can make informed decisions about infrastructure design and management. This data can help in designing structures that are better equipped to handle future climate scenarios. 3. Adaptive infrastructure. IoT enables the creation of adaptive infrastructure that can respond dynamically to environmental changes. For example, smart flood barriers can automatically rise in anticipation of a flood, protecting urban areas from inundation. 4. Resilience planning. Using IoT data, cities can develop resilience strategies that prioritize infrastructure investments based on vulnerability assessments. This targeted approach ensures that resources are allocated effectively to strengthen the most at-risk systems. Energy-efficient IoT solutions. Energy efficiency is a critical component of sustainable infrastructure. IoT technologies can optimize energy consumption across various sectors, contributing to lower carbon emissions and resource conservation. 1. Smart grids. IoT-enabled smart grids allow for real-time monitoring and management of energy distribution. These grids can balance supply and demand more effectively, integrate renewable energy sources, and reduce energy waste through automated control systems. 2. Building management systems. Smart buildings equipped with IoT sensors can optimize heating, cooling, and lighting systems based on occupancy and environmental conditions. This leads to significant energy savings while maintaining occupant comfort. 3. Transportation optimization. IoT applications in transportation, such as smart traffic lights and connected vehicle systems, can reduce congestion and improve traffic flow. This not only leads to lower fuel consumption but also minimizes emissions from idling vehicles. 4. Resource management. IoT solutions can monitor and optimize water usage in irrigation systems, reducing waste and promoting sustainable agricultural practices. Smart metering can also help consumers manage their energy and water consumption more effectively. Role of IoT in achieving Sustainable Development Goals, SDGs. The United Nations Sustainable Development Goals, SDGs, provide a roadmap for addressing global challenges, including poverty, inequality, climate change, and environmental degradation. IoT has the potential to play a pivotal role in achieving these goals. 1. Goal 6. Clean water and sanitation. IoT sensors can monitor water quality and distribution systems, ensuring safe drinking water and efficient wastewater management. This technology can also help detect leaks and reduce water loss in urban areas. 2. Goal 7. Affordable and clean energy. By facilitating the integration of renewable energy sources and improving energy efficiency through smart technologies, IoT contributes to the transition to sustainable energy systems. 3. Goal 11. Sustainable cities and communities. IoT can enhance urban planning and management, promoting sustainable transportation, waste management, and public safety. Smart city initiatives leverage IoT data to improve the quality of life for residents while minimizing environmental impacts. For Goal 13, Climate Action, IoT technologies provide critical data for monitoring climate change impacts and developing mitigation strategies. By improving resilience and reducing emissions, IoT can help cities and communities adapt to changing climate conditions. In conclusion, the integration of IoT into infrastructure planning and management presents a unique opportunity to create sustainable, resilient systems that can withstand the challenges of the 21st century. By leveraging technology, stakeholders can work collaboratively towards a more sustainable future that aligns with global development goals. The effective implementation of IoT solutions will not only enhance infrastructure resilience but also contribute significantly to the well-being of communities and the health of the planet. Appendices Appendix A. Glossary of terms. IoT, Internet of Things, a network of interconnected devices that communicate and exchange data with each other through the Internet. Sensor, a device that detects and responds to physical stimuli, for example, temperature, light, motion, and converts them into signals for processing. Protocol, a set of rules that govern the communication between devices in a network. Data analytics, the process of examining data sets to draw conclusions about the information they contain. Visualization, the graphical representation of information and data. Appendix B, IoT Protocols and Standards, MQTT, Message Queuing Telemetry Transport, a lightweight messaging protocol optimized for small sensors and mobile devices. CoAP, Constrained Application Protocol, a protocol designed for use in resource-constrained environments, ideal for IoT devices. HTTP/HTTPS, Hypertext Transfer Protocol /secure, the foundation of data communication on the web, used for transferring hypertext requests and information. AMQP, Advanced Message Queuing Protocol, a protocol for message-oriented middleware that enables communication between applications. ZigBee, a specification for a suite of high-level communication protocols using low-power digital radios for IoT applications. Appendix C, List of IoT sensor manufacturers. 1. Bosch Sensortic, offers a wide range of MEMS sensors for automotive, consumer, and industrial applications. 2. Texas Instruments, provides various sensor solutions, including temperature, humidity, and pressure sensors. 3. Honeywell, known for its industrial sensors, including pressure, flow, and gas sensors. 4. ST Microelectronics, produces a variety of sensors such as accelerometers, gyroscopes, and environmental sensors. 5. Analog Devices, offers precision sensors for industrial applications, including temperature and pressure sensors. Appendix D, Tools for Data Analytics and Visualization. Tableau, a powerful data visualization tool that helps in creating interactive and shareable dashboards. Microsoft Power BI, a business analytics service that provides interactive visualizations and business intelligence capabilities. Google Data Studio, a free tool for converting data into customizable informative reports and dashboards. Apache Spark, an open-source distributed computing system that provides an interface for programming entire clusters with implicit data parallelism. R and Python, programming languages widely used for statistical analysis and data visualization, with numerous libraries for data manipulation and plotting. Appendix E, additional resources and further reading. The Internet of Things, a look at real-world use cases and the future, a comprehensive analysis of IoT applications across various industries. Designing Connected Products, UX for the Consumer Internet of Things by Claire Rowland et al., a guide on designing user experiences for IoT products. IEEE Internet of Things Journal, a leading journal that publishes research on IoT technologies and applications. Building the Internet of Things by Masayaj Kranz, a book that explores the strategies for leveraging IoT in business. Online courses on IoT and data analytics. Platforms like Coursera, edX, and Udacity offer courses that cover IoT fundamentals, protocols, and data analytics techniques.